In this video, we calculate the change of entropy, internal energy, enthalpy, Helmholtz free energy, and Gibbs free energy when ideal gases mix. When we mix two pure ideal gases, each with the same initial pressure of P and the same temperature of T, and form a gas mixture with a total pressure of P at the same temperature T, we look at its internal energy change first. Because the mixing is between these two ideal gases, the internal energy does not change. Therefore, delta U mixing is zero. And because the potential energy of ideal gases is always zero, therefore there's no change in the kinetic energy of the two gases. And temperature is a measure of the average kinetic energy. Therefore, the temperature of the gases also remains unchanged after mixing. Assuming the initial number of moles of the two pure gases are N1 and N2, the initial volumes of the two ideal gases are V1 and V2 initially, and then we have V total after mixing equals V1 plus V2, and total equals N1 plus N2, and we have this N1 over V1 equals N2 over V2 equals P over RT equals N total divided by V total. The partial pressures of these two gases in the gas mixture are P1 times mole fraction of 1 multiplied by the total pressure, and P2 equals X2 times P. X1 is a mole fraction of gas 1, X2 is the mole fraction of gas 2. The enthalpy change equals the internal energy change plus the change of PV in the mixing process. Delta U mixing is zero. Delta PV mixing can be computed by using PV final minus PV initial. PV final is PV total, and PV initial includes PV1 and PV2. The result is zero. Therefore, there's no enthalpy change in the mixing process. In another video titled How Does Gibbs Energy Depend on Temperature and Pressure, we learned this dg equals negative s dt plus vdp. Therefore, if the temperature is constant, delta G over delta P is equal to V, and delta G is the integral of vdP. For an ideal gas, volume is nRT over P, and then we integrate this to get nRT times the logarithm of P final over P initial. Gibbs energy is an additive property, and then we have this Gibbs energy of mixing equals the change of the Gibbs energy of gas 1 plus the change of the Gibbs energy of gas 2, which equals N1 times RT times the logarithm of the final pressure of gas 1 divided by the initial pressure of gas 1, and similar here. And we sum it up, and nRT is the common factor multiplied by the sum of x1 ln x1 plus x2 ln x2. And given this delta G mixing equals delta H mixing minus T delta S mixing at the constant temperature, and with this delta H mixing equals 0, we have this delta S mixing equals delta G mixing divided by negative T. Therefore, delta S mixing is simply this expression divided by negative T, which is negative NR times the sum of x1 ln x1 plus x2 ln x2. We can derive the entropy of mixing in a different way. The entropy of mixing is equal to the entropy change of gas 1 plus the entropy change of gas 2, and we can use the entropy equation at constant temperature. Entropy change is NR, I'm sorry about the mistake here, NR times the logarithm of V final over initial, and then we use the same equation for gas 2, and V total over V1 is equal to N total over N1. We proved this before, and we reorganize this equation, And finally, we obtain the same expression for the entropy of mixing, negative NR times the sum of x1 times logarithm of x1 plus x2 times the logarithm of x2. If we have more than two gases, let's say we have a total number of I gases, where I is an integer, we can use similar derivation to get this entropy of mixing, which is negative NR times the sum of xi times the natural logarithm of xi. The Gibbs energy of mixing equals nRT times the sum of xi times the logarithm of xi. And previously we got this internal energy of mixing equals the entropy of mixing equals 0. This is also correct for the mixing of more than two gases. And therefore, we can also compute the Helmholtz free energy of mixing, which is equal to delta U of mixing minus T delta S mixing at a constant temperature. And then we have nRT times the sum of xi times the logarithm of xi. This delta A mixing is the same as the delta G mixing, only because delta PV mixing is 0. Same here. This delta H mixing is equal to delta U mixing is because the product of PV does not change during the mixing of ideal gases.